So when an amino acid is at physiological pH, I told you it is existing in this form that we call zwitterion, where it has a positive charge as well as a negative charge simultaneously. This pH, the pH where an amino acid is in the zwitterion form, pH where amino acid is a zwitterion, is called the pI. So it's written very much like pH with a lowercase p and then a capital I, pI. And you can look up the pI values for all the amino acids in a table if you wanted to. You'll never have to because they'll always be given to you for problems. So what we want to think about is what happens to the charges on an amino acid if it gets into pH, into an environment that is above or below its pI. How does that affect the charges? And the answer to that really depends on the type of amino acid that we're looking at. So the first thing that we're going to consider are the nonpolar amino acids for all of our nonpolar amino acids and our polar neutral amino acids. Our nonpolar amino acids are the ones that have just hydrogen or just carbon and hydrogen as their R group. And the polar neutral amino acids are the ones that have something like oxygen or nitrogen or sulfur, but not a nitrogen with a positive charge and not a COO. So the oxygen is in some other form. So when we have a nonpolar and a polar neutral amino acids, there's three different things for us to consider. One option for that particular amino acid would be when the pH is equal to the pI, which for these amino acids is roughly around 7, so it's approximately 7. Another option, so we're going to leave ourselves some space here. Another option would be when the pH is less than the pI. And then the third option would be, as you can imagine, when the pH is greater than the pI. So when the pH is less than the pI, that means that we're dealing with a pH that is below 7, approximately 7, and the solution is acidic, which is the name that we give to pHs that are under 7. When the pH is above the pI, then that means that the pH is above this approximate 7. And the solution is basic, which is the name that we give for solutions that have a high pH. So what do these different pHs do to the structure of the amino acid? So when the pH is about the same as 7, when the pH is equal to the pI, the COO group, let me, as we get into this, let me redraw the general structure of an amino acid over here. So we have our amino acid general structure, zwitterion form. We're going to redraw over here, NH3+, and then the R group. So when we're at the pI, the acid group and the amino group are going to exist in zwitterion form, which means that we're going to have the COO- group and we are going to have the NH3+ group, just the way that you see it drawn right here. And for the amino acid as a whole, the charge, the overall charge on the amino acid is a +1 charge for the amino group and a -1 charge for the COO-, the acid group. So overall, the amino acid has a neutral charge. Its positive charge cancels out its negative charge, and its charge is 0. So that's similar, pretty much exactly like what we were talking about in the last section. Now, if the solution gets acidic, when the pH is below the PI, things are going to change. In that case, the acid group, COO-, now exists as COOH. But there isn't a change to the amino group, so it is still going to be NH3+. So let's take a look. Let's kind of sketch out what that might look like. At an acidic pH, we would see something that looked like this. So we've had a transformation to the acid group. Instead of COO-, it's now COOH. But we haven't had a change to the amino group. So what would the charge be on an amino acid in this particular form? Well, the only charge that we have on this amino acid is just a +1 out on that nitrogen, so that's the charge. So that is what we see right here. And then the last situation, situation number 3, when we're in a basic solution, what happens then? Well, we see in that situation, the acid group is unchanged, so it is COO-, unchanged from the original Zwitter ion, comparing it to that. But this time, the amino group has been affected, so it is now an NH2 with no charge. Let's draw what that structure would look like. So we're going back to the COO-. Now we have an NH2 over here with our R group. And so what would the charge be on this type of amino acid? Well, here we only have a charge on the oxygen, and it's a negative charge, so this guy has a -1 charge. And so, as you can see, changing the pH of a solution just has, all that it has an effect on is just the amino group and the acid group. And the way that they change depends on the pH of the environment that they're in. Now, before we go on, I'm going to make a general rule here. And this is going to be a really important rule that we're going to continue to follow for all the amino acids. So this is going to be a rule. Without exception, this is just a rule. If you have an acidic pH, let's see, how do I want to phrase this? In acidic conditions. So when we have a pH pH is more acidic than PI. pH is lower than PI. The structure that we're going to draw will only have positive charges allowed. So we will never see negative charges when we are dealing with acidic conditions. And the opposite is true. In basic conditions, and this is where the pH is above the PI or greater than the PI, in that situation, we have negative charges only. So we're never, ever going to see positive charges under basic conditions. Now, depending on how strong your acid-base chemistry was in Chem 121, this may or may not be making a ton of sense to you. You did a lot of, well, maybe you did a lot of acid-base chemistry in 121, and so you might be able to look at this and just see the relationship between acids and bases and what we've got going on here. Maybe you can and maybe you can't. When you were doing acid-base chemistry in 121, you probably got familiar with some acids, some structures of acids, like H3O+, which is a very common acid that we see all the time in general chemistry. And you might have become familiar with OH-, which is a very common base that we see all of the time in general chemistry. And so, in general, maybe it wasn't shoved into your brain in 121, but in general, positive charges are associated with acids and negative charges are associated with bases. And so when we're up here with our amino acids, when we get into a situation where the amino acid is now in an acidic environment, the negative charge on the Zwitter ion form is no longer allowed to exist. And that oxygen atom is given an extra hydrogen so that it doesn't have to have that negative charge anymore because it's not allowed. And then likewise, when we are in a basic situation and in basic condition, positive charges aren't allowed. So the positive charge on this Zwitter ion has to be resolved because it's not allowed anymore. And the way you remove a positive charge is by removing one of the hydrogens. So that's kind of like a quick and dirty explanation of what's going on here.